Hello and welcome to lecture 6 of Mathematics 2. So today we are going to talk about sequences. Here is the plan of the lecture. So we have 8 parts. First of all, what is a sequence? So a sequence is a set of real numbers written in some order. Well, essentially it means that it is a list of real numbers. So it's just a list. Now we have the terms of the sequence, right? So the first element is like the first term, the second term, and so on. Then when we write it down, so we can write it down as, well, essentially as a list, like A1, A2, A3, and so on. Or we can use, well, some other notations like AN in curly brackets or AN just in brackets, something like that. So these are all sequences. But so, for example, we can write, I don't know, let's say if our sequence AN is, well, as an example, let's say it's going to be 1 over n squared, right? So we can write it like this. We can write it like 1 over n squared by n from 1 to infinity. Or we can write it as a list, like 1, 1 quarter, 1 ninth, 1 16th. Well, here the pattern is clear, right? So we could just do it like this. Or sometimes if the pattern is not so clear, so when we write a list, we can do it like this. So these are all different notations for a sequence. Sometimes our sequences can start with element that is denoted A1. Sometimes it is A0. It could start with other integers too. Yeah, so as long as it is a list, it's fine. It is a sequence. Now, if you think about a little bit about it, you will realize that a sequence is essentially a function from the set of natural numbers to the set of real numbers. Now, here is an example of a sequence. So this sequence is defined by a certain formula. What it means is that, so now if we have a formula, we can compute any element of the sequence, right? Like, for example, I don't know, let's say A24. So 24th term of the sequence is obtained if we replace n with 24 in the formula. So it's going to be 24 divided by 24 plus 1, so which is 24 over 25, which is, I believe, 0.966. All right, we can also plot graphs of sequences, just like we plot graphs of functions. So here is how we can do it in Desmos calculator, right? So if, say, we want to plot the graph of our sequence, so we need to begin with defining the intervals. I mean, so how many values of n do we want to show? Let's say we want to show values of n from 1 to, let's say, 30. So 30 elements of the sequence. Right, so the next thing is we need to define the function that specifies our sequence. So a of x is, in this case, it's going to be x over x plus 1. Now, the graph of that function is just, is going to be just a solid line that is defined for the real values of x. So it is a continuous line, right? So we don't want to do that. So what we want to show instead is this n, a, and that is going to be a sequence. So the list should look like this. Sorry. Okay. And this is the graph of our sequence. Well, it stops at the 30th element because that's how we specified it, but we can kind of see what's going on here. So for instance, we can see that the values of the sequence approach the line y equals 1, right? So they get closer. If you want, you can even write annotation here, so you can probably zoom in and see what's going on here. Like 24th term is, I computed it to be 0.26, and this is what it is, right? So 24 0.26. Okay, so this is one way to visualize the sequence. The second way to visualize the sequence is kind of, it's probably not so good, right? But so here is the first way to visualize the sequence, and the second way is like this. It's just along the x-axis, and I mean we just essentially plot points whose x coordinate is an and whose y coordinate is just 0. So we can do it in Desmos too. So if you want the second way, then it's going to be like this: a n comma 0, and this is our sequence. So it's hard to see anything, so you can probably just zoom in to see what's going on here. But um, this is what it looks like. I mean, it's just a huge mess. But hypothetically, you could do it too. You could visualize a sequence like this. All right, so let's look at some other example. So here is a sequence that is given by the equation -1 to the n, right? So a n is -1 to the power n. So what does it mean? So let me say, if we compute, say, a6, then it's going to be the product. It's -1 to the power 6. So which is the product of 6 copies of -1, right? So it is -1 times -1 times -1, -1 times -1 times -1. But notice that two negative ones give us just 1, right? So the product -1 squared is just 1. So which is why this is just 1, right? So, and if you compute, say, I don't know, 99, it is going to be -1 to the power 99, which is -1 to the power 98 times -1. And this is, well, essentially by the same argument, it is going to be the product of 49 pairs, and every one of them is going to be 1. So this is just 1. And the final answer is -1. And you see that -1 to the even power is just +1, and -1 to an odd power is just 1, right? So, and this is why this sequence is just -1 1 -1 1 and so on. If you want to plot it in Desmos, basically you can do it in Desmos too. To the x. Does it work? Yeah, this is what it looks like in Desmos. All right, so next example. So again, so we could, given a formula, we could compute any particular element in the sequence, like I don't know, 5 is -1. So we've got to replace n with 5 essentially. So to the 5 times 5 plus 1 divided by 3 to the 5. So which is -1 to the 5 is just -1. 5 plus 1 is 6 divided by 3 to the 5 is 243. Right, and again, so we could, if you want, we can plot it in Desmos. So this is -1 to the n times n, and divided by, okay, sorry, it should be x here, and divided by 3 to the x, and I guess it should be really x plus 1. And this is what it looks like. So notice that the sequence essentially becomes 0 starting after a certain term. I mean, but this is only 3 to a large power is going to be a huge number, and when you divide by a huge number, what you get is not 0, but it is like super close to 0. So which is why when you plot it, it seems like it's just 0 after some point, but it's not really exactly 0. All right, so here is the list of the elements and so on. So here we have a sequence whose definition involves cosine. And maybe before I plot it, so let me explain a little bit about what happens here. So the thing about cosine is that it is a periodic function, right? So if you take cosine of some angle alpha and you add 2 pi, so 2 pi radians is 360 degrees, right? So this is the same as cosine of alpha itself, right? So if you change the input of cosine by 2 pi, you will get the same value. Well, in our case, so notice that there is a division by 6 here, right? So if we change n by 12, then we will essentially make this operation, right? So let me explain what I mean, right? So if you want to compute a n plus 12, right? So this is cosine of n plus 12 times pi divided by 6, right? So this is cosine of n times pi plus over 6 plus 12 times pi over 6. But 12 times pi over 6 is just 2 pi, right? So this is 2 pi. So this is really just cosine of pi n over 6, which is a n. Alright, so what we found here is that a n plus 12 equals a n. Right, so this means that elements of the sequence are going to repeat after 12 terms. So, and this is what it looks like. So if you write cosine of pi x, right? So, okay, maybe, let me remove the label, right? So this is okay, delete this. This is what it looks like, right? So we have this part, then 12 terms, and then it's going to just stop. It was over 6, of course. Right? So we've got this part, and then we've got the same part, and then the same part, and so on. It's going to just repeat itself. Yeah, I guess. All right. So here is the table of values, and it's just 6 of them. But if you take 12 of them, then the next 12 are going to be the same as the first 12. Okay, so here is another sequence. So notice that here we have the square root, and sometimes the square root is undefined. So when the input of a square root is a negative number, the square root is undefined, right? So which means that if you really try to compute a0, a1, or a2, then you will run into issues, because you will get something like a0 minus 3, or a 1 or square root of 1 minus 3 or 2 minus 3. So you will get a square root of a negative number, and this is undefined. Right? So the convention is that if it is not specified, then it is going to start with the smallest integer for which the formula makes sense for that number and for all bigger values, right? So, and we see that this formula is defined for all n that are bigger than or equal than 3, because then n minus 3 is going to be non-negative. So we just assume that this sequence just begins with a3. So it is a3, then a4, then a5, and so on. All right. Okay, so I've just determined that the starting index of that sequence is 3. Right, so let me explain the starting index of this other sequence, ln of n squared minus 5. Right, so here again, so the input of logarithms should be strictly positive. So n squared minus 5 should be strictly positive. So which means that n should be either bigger than square root of 5, or n should be smaller than negative square root of 5, right? But again, since we are working with a sequence, if we worked with a function, then we should have included both into the domain. But since we're working with a sequence, and a sequence should start at some point, and then it's going to be defined for all values of n bigger than the given one. So and since so which effectively means that when we define the domain of a sequence, we're looking for something that looks like n is bigger than something, and then it's fine. So this is ruled out because we are working with a sequence. So n should be bigger than square root 5, but at the same time n should be an integer, right? And square root of 5 is, I guess, is 2 point something, right? So because 2 squared is 4, right? So square root of 5 should be bigger than 2, but smaller than 3, since 3 squared is 9, right? So which effectively means that n it starts at 3. Right, so essentially what we are looking for is we take square root 5 and then we take the ceiling function. So we take the smallest integer who is bigger than or equal than the given number. Okay. Sometimes, well, a sequence, just like a function, can be a piecewise construction, right? So it may be defined by different expressions for different sets of integers. Like in this case, if n is between 1 and 10, then n cubed is smaller than 1000. So logarithm of n cubed minus 1000 is just undefined. So we can just, okay, define Cn for those values of n to be just 1. Right. So the Fibonacci sequence is a very famous sequence, right? And it is defined recursively, right? So by this condition. So what does it mean? It means the following. It means that so we're given f0 and f1. So but then f2 is going to be f0 plus f1. So which is 0 plus 1 is 1, and f3 is going to be f1 plus f2, which is 1 plus 1, which is 2. And so on. So every next term, f3, f4, is going to be the sum of two previous terms. So f4 is going to be 1 plus 2, 3. So f5 is going to be 2 plus 3 is 5. Then we take 3 plus 5, 8. Then 5 plus 8, 13, and so on. Right? So this is the definition for this Fibonacci sequence. And generally speaking, if we have a sequence that is defined like this, it is called a recursive formula or a recurrence relation. And by the way, so Fibonacci sequence is is very famous, and if you haven't heard about it, I strongly recommend you to just Google it and read about it, because it has a lot of applications in sciences and even in biology. So I mean, it is a very cool sequence. By the way, for the Fibonacci sequence, there is a closed form relation. Fn equals some explicit explicit formula, but it is much more complicated, as a matter of fact. But anyway, so I do recommend you to do a little web search on this. Now, here is another kind of, it's not a single sequence, but it's rather like a type of sequences, right? It is a sequence of Newton's iterations for a zero of a function, right? So let me give you an example how it works, right? So let's say if f of x is, for example, x cubed minus 2x plus 4, right? And let's say we want to solve the equation this equals 0, right? So what we do, we compute f prime of x, and it's going to be 3x squared minus 12. And then we begin with some initial guess for our 0. So the initial guess, we just call it x0. So the initial guess should come from somewhere. So let's say we're going to start with, say, 0, right? So then x1 is going to be our x0 minus f of x0 divided by f prime of x0. And it is going to be 0 minus f of 0 is 4, and the prime of 0 is -2. Right, so this is 2. Now x2 is going to be 2 minus f of 2. So f of 2 is really what is 8 minus 2 times 2 plus 4 divided by 3 times 4 minus 2. This is, I guess, 8 over 10. So 2 minus is 1.2. And so on. So x3 is going to be obtained by, well, this formula. If you replace xn with 1.2, this is 1.2, this is 1.2, so then you will get x3, and so on, right? So basically, this is Newton's method of solving nonlinear equations, and uh, it not always converges. So sometimes it converges to a solution. So which means that these iterations become closer and closer to the actual answer as n grows. Sometimes it diverges. So there exist certain conditions when it converges, so we can actually figure it out in advance. And when it converges, it does it extremely fast. So like after 5 iterations of Newton's method, you will already get like 50 decimal digits or something of the answer. So, and this is how in practice computers compute things like, I don't know, let's say if on a computer you want to compute something like square root 10, right? So the computer has chips that works with zeros and ones, and essentially a computer can perform only addition and multiplication. So as far as I know, I'm not even sure that it can do division, but it certainly, so computer chips cannot do square roots. I mean, there is no such thing as a chip that, just computes, spits out the square root. So it should somehow express the square root in terms of addition and multiplication. And this is how it does it actually. So it performs Newton iterations by solving the equation x squared equals 10. Okay, so this is basically how how computers compute. Okay, so that's it for the first part. So please pause the lecture and do this little quiz.